Good afternoon, everyone. A warm welcome from einfochips. Thank you for joining this webinar on Overview of Telecom Technology 5G Infrastructure Part 2, presented by einfochips and IESA Gujarat Chapter. Today we have Dr. Yash Vasavada with us. He has done MS and PhD in Electrical Engineering from Virginia Polytechnic Institute and State University, USA. He is currently an associate professor at DAICT. He works in the areas of communication, system design, and application of machine learning algorithms to communications and signal processing. He has worked on design, development, and deployment of a number of GEO, MEO, and LEO satellites system at high-use network systems. Now, I kindly request Dr. Yash Vasavada to continue our event by sharing his valuable knowledge with us.
Hello, everyone. Thanks for joining. So yesterday we had a discussion on which we saw how the vision of 5G and 5G beyond and 6G technologies are, and how if those vision statements are realized, how the technology can usher in almost a paradigm shift in the human society in terms of, for example, virtual reality, augmented reality, mixed reality, in terms of the tactile internet, in terms of massive machine type communication that will enable smart cities and smart everything, and how it can help the industrial processes get revolutionized, because there also there will be a massive number of connected devices, and there will be not only connected devices, but there will be connected intelligence that will be ushered in because of the advances that will um, be realized in terms of wireless connectivity. And we saw yesterday that the technological goals, in order to realize this type of advances, boil down to an increase in the data rate, right? You want to be able to transmit a large number of bits per second, no matter where you are. And you want to be able to do that without exorbitant use of the bandwidth, because the spectrum is the scarce resource, and you don't want to end up using a very large bandwidth to achieve large data rate. So it comes down to the notion of bandwidth efficiency or spectral efficiency that we will talk about. We also saw that one of the goals of the 5G and the next generation communication technology is to achieve ultra reliability. And in that regard, we were looking at one technique, which is known as the channel coding or the forward error correction coding, that can provide highly reliable communication. And we were discussing this chart yesterday, which showed that there is some simple technique that you can apply, which is called rate 1/n repetition code. It is one of the simplest channel coding scheme in which either when you want to send bit 0 or you want to send bit 1, you end up repeating it n number of times. And that even intuitively, you can see that it will give you a reduced error probability, because if you have a majority voting decoder at the receiver, and if just slightly less than half of the bits, even half of the bits are corrupted, then this majority vote decoder will still be able to infer the correct bit that was transmitted. And the price that we pay to achieve that goal is the efficiency goes down, because out of every n bits, you are just transmitting only one bit of information, which is shown by this blue line. And we saw yesterday that the information theory was heralded in 1945 to 48 time period by an engineer called Claude Shannon, who showed that actually you can achieve arbitrarily low error probabilities. Basically, the number of errors that you have in your communication link, they just take a nosedive, and you do not have to sacrifice the efficiency terribly at all. In this case, suppose if you have roughly about 10% probability of bit errors uncoded, then you can convert that noisy channel, which introduces 1 out of 10 bits in error, to a channel which pretty much doesn't introduce any bits in error, in which no bits are received in error, provided that you are willing to reduce the efficiency to be about 0.53 or so. And the whole name of the game, ever since Shannon formulated his theory, has been how to bring the technology from the blue to the red. Okay, now very briefly, what I will mention is that Shannon's breakthrough idea, I think the way that Einstein revolutionized the Newtonian physics by a breakthrough idea that the speed of light is the maximum speed that can be attained. Shannon's breakthrough idea was to look at this repetition code in an n-dimensional space, right? And so if you look at that n-dimensional space, what happens is repetition code occupies only 2 points. One in which all n bits are ones, and the other in which all n bits are zeros, right? So there are only 2 points which are occupied in this rate 1 over n repetition code. And what Shannon said is that that is an inefficient utilization of the number of bits that you are transmitting. If you are willing to transmit n bits, basically if your channel code is n bit long, then that n-dimensional space you can kind of pack it up in a very intelligent manner, and then that packing of the n-dimensional space has to be done such that the information bits don't get confused with each other, right? So here in this chart, the green dots are the information code words, and the black dots are all the noisy received code words that can be received once you transmit a particular encoded code word. And Shannon's idea was to conceive of this sphere packing scheme and ensure that the different spheres corresponding to the different green colored code words do not overlap with each other. And it is that non-overlapping aspect that Shannon showed is mathematical possible is the reason why this red curve takes a nosedive. Basically, the idea is very similar to what we saw last time, where we said that if you create this type of 2 non-overlapping sets, then the information can be received without error, even though the actual channel is introducing the errors in terms of these red arrows. This is kind of a very simplistic diagram. In reality, this is not realized. There will be all this gray colored cross connects, which will introduce errors. But Shannon showed that by doing this sphere packing in an intelligent manner, you can create this 2 to the power k non-overlapping subsets in a 2 to the power n dimensional space. And now, because these subsets are non-overlapping, you can achieve error-free communication. That is the whole idea behind Shannon's theorem. The problem, as I said yesterday, was that Shannon just formulated the theorem. He didn't show how to create these green circles in an n-dimensional space. And so the art of channel coding ever since Shannon formulated the theorem has been to come up with a smart way to map a sequence of k bits into one of these green points, and then at the receiver somehow decode based on what you receive. Maybe most likely you will receive one of these black dots because of the noise. You have to map the black dot to the corresponding green dot. Okay, so that is the channel coding and channel decoding operation. Now I want to talk about the coding scheme that is used in 5G, and that is called LDPC code. Okay, so but in order for me to describe that, I will describe another very simple code, which is kind of an opposite structure to the repetition code. In repetition code, you take one bit and repeat it n number of times, and the rate is 1/n. On the other extreme, there is something called the single parity check code, or SPC code, which takes a block of n-1 bit and it adds just one extra bit, which is called the parity check bit. And so the code word becomes n bit long because of the insertion of this nth bit. And it is this nth bit which provides some degree of check, because all that nth bit is that if your information bits, n-1 information bits, if it has even number of ones, then this nth bit will be 0. If it has odd number of ones, then the nth bit will be 1. And so now when you take the resultant n bit long code word, it is guaranteed to have even number of ones, right? And so now at the receiver, you can receive an n bit code word and see whether it has even number of ones, either 2 or 4 or 6 or 8, so on and so forth. If you get even number of ones in your receiver out of n bits, then you say that hopefully nothing bad has happened, no bits have been flipped. But else, if you get odd number of ones, you know that receiver never sends odd number of ones, and so you know that at least one or maybe even more than one number of bits have been flipped. So basically there are n-1 information bits, total number of encoded bits is n, and so the rate is n-1/n. And as n becomes large, this code is highly efficient. The rate becomes almost close to 1, right? n-1 divided by n becomes very close to 1 if n becomes large. And so unlike the repetition code where n becomes large, r drops drastically, quite an opposite situation occurs here, where as n becomes large, r becomes closer and closer to 1. Basically, you get highly efficient channel code. The problem is that this channel code is very weak. It cannot do the error correction very well at all. Okay, so this is just a diagram for me to represent how the SPC code works. This is a rate 3/4 SPC code. There are 3 message bits or information bits, M1, M2, M3. Is 1 parity bit. So the total code word has 4 bits, C1 to C4. Rate is 3/4. And this S1 is called supervisory check. All that it does is the sequence of 4 bits, C1 to C4, it checks whether it has even number of ones. And if it has even number of ones, this supervisor is happy. And it will be equal to 0. If there are odd number of ones, then this S1 will be equal to 1. And it implies that the parity check has not been satisfied. Okay, so that is what we talked about, the repetition code and the SPC code. Okay. Now, in 1950s, a number of better, more intelligent coding techniques were devised. The 2 prominent ones are called Hamming codes and the Golay codes. Then in late 1950s, maybe early 1960s, some more refined coding schemes were developed. For example, there is a coding technique called convolution code. There is a coding technique called BCH codes, and that name comes from the first letter of the last name of the inventors of this coding scheme. BCH is Bose, Chaudhary, Hockenhagen. Bose and Chaudhary were Indian mathematicians. Hockenhagen was a German mathematician. They together developed this BCH code, which leverages the ideas of abstract algebra and the Galois field, the groups, the rings, etc. It's very sophisticated math concept. But BCH codes are far more powerful, far more efficient than this repetition and the SPC codes that we have talked about. Subsequent to BCH code, the next family of codes that were invented are called Reed-Solomon codes, again invented by mathematicians Reed and Solomon. Then later in 1960s, early 1970s, Forney in the USA developed the concept of concatenated coding, where he would take maybe a convolution code and the Reed-Solomon code, and he will connect them back to back. And through that, he was able to achieve good performance. The problem is that in order to get better and better performance, the price paid was increasing computational complexity. Now I'm glossing over a lot of the development that happened in 1970s, 1980s, etc. And I will directly jump to 1990s. Okay, in 1990s, somewhere around 1993, there is a very prominent conference that is organized once a year worldwide. I mean, it happens at different locations throughout the world every year. In 1993, in this conference, ICC, International Communication Conference, a group of French engineers, they wrote a paper, they presented a paper on turbo codes. Okay, so they are the inventors of turbo codes. And actually, these engineers who developed the turbo coding scheme, they were not even communication engineers. They were not even coding mathematicians. They were actually FPGA engineers, VLSI engineers, maybe like a lot of the attendees today. They were actually trying to implement some coding architecture on an FPGA, and in process of doing that, they got interested in how the convolution codes work. And they came up with some smart way of concatenating two convolution codes and then exchanging the output of one convolution decoder with the other. And then the output of that second convolution decoder, they would send back to the first convolution decoder. So they would create this at the decoder, there would be like a feedback loop that was established between these two convolution coding process. That was their idea. They ran some simulations and the results that came out were magical, right? All the way until 1970, 1980, so many different mathematicians came up with some really smart ideas, but they were not able to crack the problem completely, right? In order to come close to that red line, they had to ask for an inordinate amount of computational resource, which was just impractical. But in 1993, this group of VLSI engineers came up with this turbo coding technique, which was computationally feasible, and it did a far better job than the previous techniques in terms of approaching the Shannon limit. And so turbo codes gained a lot of attention. There was a lot of excitement in the air. A lot of different organizations, research organizations in academia, as well as in the industry started simulating turbo codes, implementing turbo codes. And then finally, in the 4G today, when you talk on your phone or when you browse the net, Without your knowledge, it is a turbo coding scheme which is ensuring that your communication does not suffer from large number of errors. Okay, so that was one challenge that was solved. Then about 2 years later, or approximately 1 or 2 years later, another group of mathematicians, David McKay and his collaborator, I forget his name right now. He's a mathematician based in Canada. They developed another coding scheme which was working equally well, if not better. And so they published their paper and they called it some name. But when other scientists and engineers started looking at McKay's idea, they realized that the exact same idea was earlier formulated all the way back in 1960s, actually 1960 and 1961 by another statistician, mathematician called Robert Gallagher. And that time he had given this scheme the name low density parity check codes. And so McKay's kind of limelight was kind of stolen from McKay. He was called a rediscoverer of LDPC codes. But the credit for the original invention of LDPC goes to Gallagher. What happened was 1960s, the computational resources were very weak, right? The ASICs and FPGA technology was pretty much non-existent. And LDPC codes, although they're very efficient and computationally also they're very good, the technology was simply not there to implement LDPC codes in those days. And so after Gallagher proposed his code, people looked at it and they said, well, maybe, yeah, this can do the job. But even the computers of those days were not powerful enough to simulate the LDPC codes in its full strength. And so people didn't get excited as much. Everybody forgot about LDPC codes until McKay accidentally kind of came upon or stumbled upon the same idea. And when McKay ran his simulations in mid-90s, he had powerful computers, and so he could show that LDPC codes do come very close to the capacity bound. Okay, so that is where the state of the art is. Today, going from 4G to 5G, the turbo codes are getting replaced by LDPC codes because LDPC codes are slightly better than turbo codes. Okay, both in terms of implementation efficiency as well as the performance aspect. So what is LDPC code? We'll take a very, very quick look at it. It turns out that LDPC codes is made up of a large number of repetition codes and SPC codes. That is actually all there is to it. We don't have to go to Galois field or rings and the concept of the various concepts of abstract algebra which are required if you want to understand, for example, read Solomon code or BCH codes. For LDPC, the whole idea is that you put a bunch of SPC codes, you put a bunch of repetition codes, and you connect them, interconnect them. And then you keep on exchanging the error correction performed by one code with respect to the other, and then back. Okay. So that is what the LDPC code is. It is called low density because it's something called parity check matrix, has a very small number of ones. This parity check matrix, you can think of the rows of the parity check matrix as performing this SPC coding, right? The rows can be viewed in terms of this diagram, and the columns of this LDPC H matrix, which I'm showing here, the columns can be thought of as the repetition codes. Okay, so that is what it is. What happens is that the decoding of this code can be made highly efficient, especially on a parallel processing. So, For example, I can take this H matrix and I can convert it to a graphical model, right, which is shown here. You will see that there are 1, 2, 3, 4, and 5 supervisory nodes. What it means is that if I look at this H matrix, it will have 5 rows. I mean, this H matrix will have a different graphical realization. But if I consider an H matrix with 5 rows, then those 5 rows will represent this S1 to S5. Basically, each row is a single parity check code. And this is called the bit nodes or the variable nodes, and they represent the columns of this H matrix, right? And all that this variable nodes are repetition codes. And the way the decoding works is you first take the output of a channel, and maybe some bits are in error, so that is what this E represents, and some bits are correctly received, and you send those bits to their supervisors. And the supervisors will say that, okay, I am not happy, I am not satisfied, my parity is not even. And so it will turn the erroneous bit into a correct bit. And that type of message exchange will go from one supervisor node to the other. And then eventually, even the variable nodes will start broadcasting their message to their supervisors. And eventually, after several iterations, all the errors or the erasers will be resolved, right? So initially you had maybe as many as 5 errors, 1, 2, this one was in error, so 3, 4, and 5. And then after a few iterations, all of them have been corrected. And the way this happened was there was a message exchange that happened. All these green and blue colored lines that are representing the messages that go from the variable nodes to the check nodes. This message basically tell the check nodes that, okay, this is my value. And then check node sends a message back to the variable node by this blue line, telling the variable node that, okay, this should be your value, right? So it's like a lot of interconnect communication is happening between the variable nodes and the check nodes. Maybe one analogy would be that you are in a room full of people, there is a speaker giving a speech, but there is a lot of noise. So different people hear different parts of the speech, but then they exchange messages among themselves, telling each other what they heard and correcting the mistakes in what other people heard. And eventually the entire network of attendees in this conference room eventually understands the entire speech, although individually they all got a lot of the speech wrong, right? So that is the type of message exchange, or what is known as message passing, that happens on the graphical representation of the LDPC codes. So I just wanted to give you a flavor of the technology behind the 5G LDPC technique. And there are many mathematical analyses that have been done to evaluate the performance of an LDPC code. But one such analysis, which is shown here, says that if suppose my error rate is 30%, as large as 30%, right? And I have an LDPC code with an SPC structure, which is basically an SPC code which is 6-bit long and repetition code which is 3-bit long. So this will be a 5/6 SPC. This will be 1/3 repetition. Then even the code word that I receive has 30% of the bits in error. So that 30% is over here. After about 7 iterations, all the errors will be corrected. Right? If I have 35% of the bits in error, then I will need a few more iterations. But by maybe about 10 iterations, again, all the errors will be corrected. The yellow represents 40%, then 41%, 42%. As many as 42% of the bits in error, they also will get corrected by about 30 iterations. If you end up having maybe 43% or 44% bits in error, then now this scheme will not work and the errors will remain unresolved. So this is an example of the powerful error correction that can be done using an LDPC code. Okay, now I will switch over to my presentation from yesterday. Okay, so what we talked about is how Shannon formulated his theory of error-free communication in presence of noise, and how there was an intense effort over a number of years, culminating maybe in 1990s, early 2000, where some of the promises that were formulated by Shannon were starting to get realized. And we looked at that repetition code, and we compared it to that red line, which was Shannon's binary entropy function, and we saw that there was a big gap between the two. And the LDPC codes, as an example, they kind of bridge that gap. Now, if you read Shannon's paper written in 1948, you can do a search on this title of the paper, A Mathematical Theory of Communication, and you'll see a lot of links will come up. It is one of the most highly cited paper, by the way. It's very well written, so actually if you spend a little bit of effort, you will be able to understand quite a bit of the paper. The way I think of Shannon's work is in two parts. Okay, so one part is what we already saw, right? Formulation of binary entropy function, which allowed us to draw that red colored line that we looked at yesterday. But to formulate that theory, Shannon considered just binary transmissions for most of the cases. And he really didn't invoke the actual physical communication transmitter and communication receiver. That he did in the second part of this paper, where he said that my messages need not be binary anymore. He called it a set of messages, and it can be, there can be two messages, then it will be a binary message, 0 or 1, or it can be 4, or it can be 8, or it can be 16. It can be however many different messages that you want. It can be even the letters of letters of English alphabet, or letters of Gujarati alphabet, or it can be different colored pixels of an image. All of those, he called it just messages. And he said that whether you transmit 0 or 1, you are actually selecting from a binary set. But if I will generalize it and say that the set need not be having just 2 elements, it can have any number of elements. But ultimately, the information is generated when the source of the information selects one of those messages. And then he said that that selected message has to be mapped to an actual physical signal. It can be an electromagnetic wave, it can be maybe even a sound wave. That signal then goes over the communication channel, which invariably corrupts it because of the noise. And so what communication receiver sees is a noisy version of the signal. The signal is now not bits anymore. It is the actual transmitted signal that comes out of, for example, an antenna. And this noise is not simply this binary symmetric channel type of noise where bits were getting flipped. This is the noise that you, for example, hear when you turn on your radio and you're tuned to not any radio station and you just hear the static. Right? So this is the real world noise. And he said that this is now the problem that I will solve. Now, the way I like to think of the work that he did is, again, compare it with Einstein's work, right? So Einstein wrote two papers. One was on spatial theory of relativity, which was written in 1905.
Have attention, please. This is to just inform you, food and beverages are strictly prohibited on work area. Please avoid them on work area.
Right, so
Attention, please. This is to just inform you, food.
so spatial theory of relativity was written in 1905. And then Einstein took that to a completely a new level, right? And he formulated general theory of relativity in 1915. And many physicists have said, have expressed an opinion that maybe they could have come up with the spatial theory of relativity, but to solve the general theory of relativity was just mind-boggling. It basically, Einstein took the game to a whole new level, right? Same way, Shannon, when he formulated the theory of binary entropy function and he drew that red line that we were looking at last time, it was a problem that he himself conceived and he solved, but many communication engineers have afterwards said that that is something that they could have thought of. Okay, that was a brilliant insight and very impressive mathematics, but it was still within the realm of the mere mortals like the rest of us. But then Shannon took the game to a whole new level, which many smart mathematicians after him have said that they don't know how he came up with the theory and the proof and the idea, which allowed him to extend his first part of the paper to the second part, where the problem statement is highly complex, very difficult to solve. It was just a sheer stroke of genius by some extremely capable, very smart, very intelligent mathematician. And he actually ended up solving this problem, and the formulation of the problem in terms of the parameters is what we today, even 70 or 80 years after he wrote the paper, or I shouldn't say 80, it's actually 74 years after he wrote the paper. Remember, in those days, there were no wireless communications systems. The radio systems were also just beginning, right? The human society had not seen all of the communication related advances. In those days, for him to imagine the type of metrics that even a common person today, a layman, fully understands, right? The bit rate in bits per second, the spectral width or the bandwidth, W, or sometimes it is called B in hertz. These are something that we understand today, right? He formulated the problem in terms of these parameters. And he said that if I want to get a certain amount of bit rate, when I am given a certain amount of bandwidth, then what will matter is how much signal to noise power I have. PS over PN. And we will not get into the mathematical idea that Shannon had, but the final outcome of his analysis, at least in what is known as additive white Gaussian noise, is given by this equation. He said that the bit rate R in bits per second can never exceed the product of bandwidth W times logarithm base 2 of 1 plus SNR. Okay, so that is his magic formula. This is sometimes called E equal to MC squared of communication theory. And I've plotted this formula as a function of SNR, PS over PN. And I have actually, what I have plotted is the ratio R divided by W, bits per second divided by hertz. And it turns out to be this blue line. And this is called the unconstrained limit, 1 log base 2 of 1 plus SNR. SNR is sometimes also written as ES over N naught. And so what Shannon formulated is that you cannot cross this blue line. And the challenge that he formulated was that the communication system should operate as close to the blue line as possible. Okay. Now, few things that I'll very quickly mention. You want to operate at a lower PS over PN, because typically PN, the noise power is given, and you don't want to transmit a large number of signal power. Because if you transmit large value of PS, then it means that you are asking for a bigger power amplifier, bigger antenna, maybe a bigger battery. And so one of the goals of 5G and extensions is to operate at lower values of PS. Now you will see that if I reduce value of PS for a given amount of PN, it means that I'm going leftward on the x-axis. That is good. That means that I'm being more efficient in terms of power. I'm using power more efficiently because I'm asking for smaller and smaller values of power to be transmitted. That means that my battery life can be prolonged. That means that my antenna size can be reduced. My power amplifier specs can be relaxed. So that is all good. But then you will see that if I start moving leftward on the x-axis, meaning that I improve the power efficiency or the energy efficiency, then I'm forced to go down on the y-axis. Right? The blue line will start dropping. And that is a problem because now for a given amount of bandwidth in W, I will be able to transmit smaller and smaller data rate in bits per second. And so y-axis is called the bandwidth efficiency. And what Shannon showed is that this energy efficiency and spectral efficiency are kind of in conflict with each other. If you want to improve energy efficiency, then you have to sacrifice spectral efficiency and vice versa. Now, let us look at the capacity curve that we were looking at here and relate it to these performance goals going from 4G to 5G. This slide we had seen yesterday, right? The yellow is 4G, the blue is 5G. And you will see all of the metrics, data rate, the peak data rate, the user experience data rate, the spectral efficiency, the connection density, the network energy efficiency, traffic capacity, all of this are ultimately either the x-axis or the y-axis. The energy efficiency is x, the data rate, the spectral efficiency, the per user data rate. Those metrics are simply the y-axis of that plot. Only thing that are not captured in that plot are user mobility and latency. Other than that, everything else ultimately boils down to what Shannon formulated in 1948. In 4G, there are three technologies. As I said, one is turbo codes, the other is MIMO, and the third one is OFDM that we will look at how they realize the technological goals, right? Now, due to lack of time, I couldn't prepare the data for 4G, but I have something which is quite similar, and that is for equivalent communication scheme in the satellite communication. So this is how SATCOM scenario looks like. Okay. This is this green line here, right? It is the unconstrained limit, log base 2 of 1 plus SNR. I've taken a small segment of it in this region. So that is the green line. Now, Shannon's formulation of the green line considers kind of a highly capable transmitter that has no computational constraints. The realistic transmitter has some modulation constraint, and one example modulation is called QPSK. And so afterward, after Shannon formulated his theory, some statisticians took his theory and said that, well, if the transmitter were to transmit only QPSK signal, then what would the limit be? Because of the constraint imposed by QPSK structure, you cannot achieve green line at all. Maybe at very low SNR, maybe you can achieve green line, but otherwise, the best you can do is this blue line. This square over here is where the technology was equivalent of 2G. Right? It used convolution code with constraint length k equal to 7. This is something that was possible in the days of 2G. And then the technology kept on progressing. From k equal to 7, the technology went to k equal to 9. Then some other variant of k equal to 9. Then came the turbo codes, which are the blue stars, and then the LDPC codes, which are these triangles. And so you see that the technology kept on coming closer and closer to the blue line. Right? This is the progress that happened effectively from 2G days to around 3G or 4G. Yet another visualization of the same thing. On this side, I have this table, which is known as mode code table. This is part of the DVB-S2 standard, Digital Video Broadcasting over Satellite version 2. On the right-hand side, again, I have drawn the unconstrained limit formulated by Shannon, and then where the different modulation and coding schemes of this table operate. So all of these colored markers are different rows of this table. So you see that the technology is coming closer and closer to the blue line over the entire range of SNR. But then subsequent to DVB-S2, which was formulated in early 2000, maybe about 20 years back, the engineers developed something called DVB-S2X, the extended version of DVB-S2 around maybe 8 years ago. And that is again shown with respect to the unconstrained capacity limit. The red is the advance that happened in 2014. The blue is where the DVB-S2 standard was in 2000. So you see that a lot of the engineering happens going from 2G to 3G to 4G to 5G. Ultimately, it boils down to bringing the operating points closer and closer to the unconstrained bound. You'll see that in DVB-S2X, even the red points are still away from the Shannon limit a little bit. They are not very much away like how the technology was maybe before the invention of turbo codes or LDPC codes. But now a lot of the people are trying to close even this little bit of gap that is remaining. Okay, for the sake of time, I will skip over this slide, which shows the details of the improvement that was achieved in DVBS2X over DVBS2. And I will now move on to MIMO technology. I have about 5 more minutes, so I will try to cover very quickly my remaining slides. Okay, in 4G, starting 4G, subsequent to 3G, the standards, the terrestrial communication standards, started incorporating what is known as MIMO technology. It is multiple input, multiple output system. Basically, all it is that instead of using just one antenna at the transmitter and one at the receiver, in the MIMO system, there are more than one antenna at the transmitter and maybe more than one antenna at the receiver. Okay, so this should have been one. So the channel between the transmitter and receiver looks like this. Each transmit antenna sends the signal to each of the receive antennas. So this side is the transmitter, this side is the receiver. These arrows are showing the antennas, and the red lines are showing the connectivity between these antennas. Right, so each transmit antenna sends the signal to each of the receive antenna, and each receive antenna listens to each of the transmit antenna. And so basically the channel for a MIMO system can be represented as this H matrix, which is actually an NR cross NT matrix. Somewhere around 1997 or 98, again in the same lab that Shannon worked at in 1940s, the Bell Labs in New Jersey, another group of engineers came up with an idea that instead of using just one antenna at the transmitter, one antenna at the receiver, if we use multiple antennas at the transmitter and the receiver, basically use this MIMO system, then without using any extra bandwidth, I can transmit far larger data rate, maybe as much as K times the data rate. And the way they were able to show that was again by using some advanced topics of linear algebra known as SVD. If you're familiar with SVD, then maybe this diagram will make a little bit of sense. But basically what they showed is that if we do the singular value decomposition of this MIMO channel matrix, it turns into a bank of these parallel channels, and you can transmit data parallelly on each of the channels. If there are K channels, then you get K times the data rate. And this was a major advance because now my spectral efficiency, my bit rate, the amount of data rate that I can achieve goes up by a factor of K. Some math is shown here. It basically says the same thing, that without extending the use of bandwidth B in hertz, I will be able to transmit NR times the data rate. Right, the spectral efficiency equation that Shannon formulated, it gets multiplied by NR, supposing that this K is equal to NR, the number of receive antennas. And this is very impressive because suddenly your capacity bound just shoots up. Right, so this gray line is the gray line is without the use of MIMO, and this dotted line is if you use 4 transmit antennas and 4 receive antennas. And so you see that for the same SNR, and without using any extra bandwidth, I'm able to transmit as much as maybe 4 times the data rate. So this was kind of a paradigm shifting moment. I was just starting out as a communication engineer in around the time that the news broke that these engineers from Bell Labs have come up with this MIMO concept. And they were pretty smart engineers. They didn't only develop this math, which is on this slide, but they actually even developed a POC in their lab. They showed actually using actual hardware that they were getting this performance improvement. And so ever since then, people are talking about MIMO even today. Okay, so MIMO is a way to realize the technological vision that was stated earlier. The challenge is that in order to get as many as k different singular values, where k is a large number, as maybe as large as the number of receive antennas, the antennas first of all have to be sufficiently separated. And the second is that you need to have large number of antennas. If you are having a handheld device, how to have more number of antennas is a technological challenge. The third topic that I will very quickly survey is called the OFDM, orthogonal frequency division multiplexing, which is used in 4G, and also some enhancement of OFDM is going to be used in 5G as well. For the lack of time, I will not get into the math, but I'll just mention that OFDM very efficiently solves the problem of inter-symbol interference. Okay, inter-symbol interference occurs when the wireless channel generates echoes. It generates multipaths. In this case, there are a total of capital L multipaths, and they come and superimpose on top of each other. And when there are echoes, you know, if you have heard any, if you're in an auditorium which is generating a lot of echoes, how difficult it is to decipher the speech. To overcome the effect of echoes in wireless channel has always been a burning problem for communication engineers. And there is some math here. Actually, the math makes use of a similar concept, not the singular value decomposition, but the eigen decomposition. And it uses some very smart ideas from the linear algebra topic. And it combines them with the FFT and the inverse FFT operations, which are computationally very efficient to be realized on an FPGA, for example. It combines all of those ideas, and as the end result, it kind of solves this ISI problem in a very smart manner. Essentially, OFDM transmits the signal or the symbol or the information in frequency domain by use of DFTs and inverse DFT. And sometime in 1980s or 1990s, the mathematicians who came up with the OFDM concept showed that by doing that, they can diagonalize this channel matrix through the eigen decomposition. If you want to understand the math, it is all here. Right now, I don't have time to go over the math, but I'll give a summary. What an amazing and powerful way the mathematical concept underlying OFDM was, right? What happened was, before the OFDM technology was fully mature, in 2G, in 2.5G, in 3G, the waveforms that were used were non-OFDM, right? If you have ever used GSM phone, it was not OFDM phone. It was using multi-carrier TDMA. In the USA, maybe in Korea, maybe in some parts of Europe, the technology was based on CDMA. Right? There's a company called Qualcomm, which was a champion of CDMA in those days. So starting from around 1990s to maybe early 2000, maybe those 15 years or so, all the technology was based on non-OFDM methods. And there are maybe exaggerating, but maybe there were hundreds of thousands of engineers who worked on the TDMA, the FDMA, the CDMA ideas. They developed the simulations, they developed the math, they developed the implementation designs on ASICs and FPGAs, on DSPs. There was a whole lot of infrastructure, right? There was maybe a multi-million-dollar investment, maybe even I will, at the risk of exaggerating, I will say multi-billion-dollar infrastructure development that happened, and OFDM came and replaced it in one fell swoop, right? That is the power of this math. Why did industry give up on all this investment that it made? And why did it build OFDM from scratch, starting 4G? The reason is the diagonalization of the channel matrix. So if you have learned linear algebra in your college, and if you remember this concept of eigenvalue decomposition, well, that time maybe you thought that, okay, it's some abstract math. But the elegance and the power of that math was such that it overthrew this multi-million, multi-billion-dollar infrastructure. And in its place came OFDM, which allowed a far simpler receiver implementation. The cost, the complexity, the battery life, there was clear benefit in all that, right? The management and the engineers, they were human beings, right? Nobody would want to give up on the investment that they would have made unless there was a compelling reason. And OFDM showed that there is a great benefit to be obtained if you do this matrix diagonalization. Okay, so that is the OFDM. I think I'm run out of time now. I have some more slides on the network level aspects of 4G and 5G and even 6G. I think I'll skip over these slides and I'll conclude my talk here. In case if you're interested, the slides I think should be made available to anybody who is interested. Or you can send me an email and I will send you the slides in case you are interested in this latter part of this presentation. Okay, thank you for listening. I'll take questions if there are any now. Okay, so there is actually only one question today. Somebody has asked that as I understand, LDPC codes would be correcting messages based on some parity symbols. Along with the data, parity symbols also get corrupted in channel. How does LDPC code work in this case? So the LDPC codes actually don't distinguish between the message and the parity. All it does is it tries to bring the entire code word to. So when the LDPC receiver receives a sequence of n bits, some of those bits will be incorrect. And as a result, when you put those bits on the tenor graph at the bottom, some of those supervisory checks that I was showing, S1 to S5, if you recall, they will be unsatisfied. Basically, some of those checks will be saying that, well, the bit nodes or the variable nodes that are connected to me, they don't have even parity. There are not enough even number of ones. And so those supervisory nodes will flip some bits so that at that particular node is satisfied, and all the bit nodes connected to it have even number of ones. But when one supervisor node flips some bits, the other supervisor node, which is connected to at least some of those bits, will now say that, okay, no, now my parity is not satisfied. So it will in turn flip the bits that are connected to it, and so on and so forth. So that process will iterate. And eventually, if the decoding is successful, what will happen is all the supervisor nodes will be happy. They will say that my parity checks are all satisfied. That is when the decoder says that I have done my job. All my check nodes are showing even parity, and the decoder comes to a full stop. This is called hard decision decoding. The actual LDPC decoder in your phones and in your wireless devices operates in a little more smarter manner. But I'm just giving you the idea in order to answer your question that in this decoding process, it doesn't matter whether the corrupted bit is a message bit or parity bit. Okay. What is the main difference between 4G and 5G? Okay, there are many differences. If you look at that 7-layer OSI type of model, there are improvements and enhancements that have happened going from 4G to 5G in pretty much each of those layers. What we have talked about is mostly the physical layer. And there, at the physical layer, the improvements are at the bottommost layer. The improvement is in terms of achieving the Shannon bound in a more efficient manner. So 4G was using turbo codes, whereas in 5G, the LDPC codes are better than the turbo codes, both in terms of computational aspects as well as performance aspects. Turbo codes sometimes suffer from what is known as error floor. At very high SNR, they don't perform as well, whereas LDPC codes do not have an error flow. In LDPC codes, that Tanner graph model that I was showing, the check nodes and the variable nodes, they are individually very, very simple operations. Right? Parity check just says, okay, whether I am seeing even number of ones. The repetition code just says that whether all the bits that I'm seeing are same or not. So individually at a check node and the variable node, the operation that happens is simple. Collectively, if you look at the entire LDPC code, maybe as long as maybe 10,000 or 20,000 bits, which is in 5G NR, then collectively there is a massive amount of computation that is happening in those iterations. But the idea behind LDPC code and the reason why they are better for implementation aspect compared to turbo code is that all of those nodes of Tanner graph, the check nodes and the variable nodes, they can be operated in parallel. Right? So the parallel implementation aspect is one reason why I was on mute all this time. Okay. Right. So going from turbo to LDPC in 5G, there is another coding scheme called polar codes, which we didn't even get into. So that is one advancement that has happened going from 4G to 5G. The MIMO technology has become more powerful in 5G compared to 4G. In terms of frequency of operation, there is something called millimeter wave operation, which is a far higher frequency compared to what is used in 4G. That millimeter wave operation, again, allows the realization of an improvement in spectral efficiency. And also the channel realization also changes. So those are some of the changes that that are going on in terms of physical layer. At higher layers, there is a whole lot of advances that I had mentioned in my slides that I couldn't finish today. So those are some of the changes that have happened in 5G compared to 4G. I don't think that I can identify that there's just one difference between 4G and 5G. There is a whole lot of technological advances that have happened going from 4G to 5G. If someone is changing from 4G to 5G on infrastructure side, do they have to replace hardware in the system? Okay, so this 4G and 5G are fuzzy terminologies. There is not a very clear-cut boundary between 4G and 5G. In terms of standardization, this is called LTE, long-term evolution. And so even what we call 4G today, it is better than what 4G was maybe 5 years back. Right? So there is incremental addition of this better, newer, more powerful features in the standards. So there's the entire standard is called the 3GPP standard, and the standardization body meets maybe once a year or every 18 months or so, and every time they formulate some advances. And after enough number of advances have happened, then what we will get is what is colloquially known as 5G. But there will be an intermediate state where you will be kind of straddling both the 4G and the 5G arenas. But yes, there are certain aspects where if you have, for example, millimeter wave technology at the base station, and if the phones don't support millimeter wave, then you're not going to get that benefit of millimeter wave. The massive MIMO is another such technology, right? There are hybrid scenarios, but as more and more infrastructure starts moving to 5G based infrastructure, then everybody will have to eventually come on the board. Okay, I think that is pretty much it. What are challenges for 6G? I don't know how to answer that question. What are challenges for 6G? What I would say is that, as we saw yesterday in the first half of my presentation, the technological goals are kind of all the way up here, right? There is not going to be any lack of demand in terms of achieving higher and higher data rates, increasingly more accurate communication links that use smaller amount of bandwidth and smaller amount of power than what is possible today. Right? So the technological goals are always going to be very high, up in the sky. And how to realize them, especially given the limits that Shannon has imposed, right? Those unconstrained capacity limits that we were looking at, is always going to be a challenge. So MIMO opens up one new arena where that limit itself can be elevated. But then there is a lot of development that needs to be that needs to happen in terms of the back-end side, right? The infrastructure also has to become modernized. And there are concepts known as softwareization and virtualization. There are concepts known as the cloud RAN, right? So the actual hardware that you would see, maybe the base station or the antennas at even mounted on a rooftop, etc. There will be very dumb devices. All the intelligent processing will be happening in the cloud. So Cloud RAN is one such technology. There's something called the concept of network slicing. There's some other technology called SDN, uh, uh, software-defined networking. There are a lot of rapid advances that are happening in the back end, right? This is not something that you would see directly implemented on the hardware that you are touching in front of you. So I think there is no dearth of challenges in terms of 6G and maybe even next generation of communication advances. Okay, so I think that is all. Thank you. Thanks for your time, and thank you for listening. I think somebody has asked that how do we get these slides? I do not know the answer to that. Do you know how will the slides, will they be made available? Is there a way? Yeah, we don't know that. Yeah. You can send me an email. If you go to my webpage on DICT, you'll find my email. You can send me an email and I can send you the slides. I can email you the slides. Or maybe I'll put the slides on my webpage later this week. And so you can simply download it from there. What are the reasons for EVM failing in 5G? I don't know. What is EVM? I don't know what is EVM. EVM, the term that I know is error vector magnitude, but I don't think that is what you are asking. So I don't know the answer to this question. I think we are done. All right. Thank you all. Bye.
Thank you, Dr. Yash Vasavada, for sharing your valuable knowledge on 5G.
Dipesh.